All right, so let's continue this quite boring topic, computational cost. But we do need to figure out who costs more, who costs less, before we can make a list who to deal with first, right? The priority list. And we talked about Jacobian evaluation. Then after you computed Jacobian, you have to do Gaussian elimination to solve the linear system. Okay? Ax equal to b. If you want to solve the linear system, you can do A inverse, right? Inverse matrix, or do Gaussian elimination. So time is similar. It's a cubic function. So basically, the time it takes for LU factorization or for matrix inversion is a cubic function of a number of species, n cube. So therefore, if you put n cube here, so I didn't put it here. The reason is so far for a lot of people, they only try the detailed models up to, let's say, 2,000-3,000 species. So far for 2,000-3,000 species, we haven't found the LU factorization actually takes more time than numerical evaluation, numerical perturbation evaluation of Jacobian yet. So because numerical perturbation for Jacobian, each perturbation you need to evaluate a lot of exponential term in the Arrhenius rate, right? But for factorization, it's pure linear algebra. There's no exponential function to evaluate. So it's a lot faster actually. So therefore, unless you have a very large matrix to deal with, let's see more than 3,000 species, then you don't see the cost become n cube. Okay, but if you change your Jacobian from numerical perturbation to analytic Jacobian, you can see clearly a cubic trend. So we'll show that later. So therefore, I just didn't bother to put this k cube yet. So let's see. This is the most time-consuming part. You need to get rid of the Jacobian evaluation first, and then here this is Jacobian evaluation. So how about the rate evaluation? Rate evaluation, as I said, it's a linear function of number of species or number. So compare this guy with this guy. This is nothing. So therefore, people typically don't complain about the 1 or 2 rate evaluation. It doesn't matter too much, right? And then, in addition to this, you need to compute the diffusion term. The diffusion term, if you think diffusion is basically is a boundary collision process. So diffusion was even intrinsically happening through molecular collisions. So intrinsically, diffusion process is pairwise. If you get n species, you need to evaluate the diffusivity of n square matrix. So diffusivity, particularly the boundary diffusivity matrix is a square matrix. Each entry is kind of complicated, but people can use exponential function to tabulate this temperature dependent part for that. Okay, so therefore for diffusion, the cost will be a quadratic function of number of species. So this is pretty much how much time it takes for models with less than 2,000-3,000 species. Of course, the most effective way you deal with it is to get rid of the numerical Jacobian. That's the easiest one you can do, and it's most effective. But when this is gone, the next one coming up, of course, you need to handle is this guy to get rid of the quadratic term, right? So the diffusion matrix, then we need to consider how to simplify the diffusion process. So we will have one section just to talk about how to almost get rid of this cost. This can be gone, okay? And then when this is gone, this is gone. The only time left is the time needed to evaluate reaction rates. So it's a linear function of a number of reactions. So therefore, with analytic Jacobian, it's possible to make the computational cost a linear function of a number of species. So years ago, we couldn't do this, but right now we can do it. But in comparison, if you deal with explicit solver, each step you only need to evaluate the rate. So the only time it takes is rate evaluation together with diffusion evaluation, which is, this is square matrix, this is linear function. Again, if you can deal with diffusion efficiently, the only cost left will be evaluation of chemical rate. So therefore, the limiting case for whether it's an implicit solver or explicit solver, the best case you can do is bounded by the rate evaluation. That's the minimum time you have to spend. You have to at least compute a set of reaction rates before you can march with time, right? But the key challenge for using explicit solver is how to handle or how to deal with the short time scales associated with those fast radicals or partial equilibrium reactions, okay, the isomerization reactions. So we will deal with this next, and this one we have a look at it. So this figure shows something very interesting and also very useful for Jacobian, because as we said, in addition to evaluation of Jacobian matrix, we also need to factorize it. Factorizing it, eventually we find it's not that big a deal, because previously we believe it's a cubic function of the number of species, so n cubed. But it turned out if we take advantage of something interesting here, which is the sparse pattern of Jacobian, actually the factorization is no big deal. You can do it in linear time also. So the factorization or the Gaussian elimination can also be done within linear time. So that would be a much better scenario then. So, but why Jacobian matrix is sparse, if you think? Yeah, you can imagine this way. Let me just put this back. I bring up it's just so annoying. It's just something. Nah, never mind. Okay, let me just move this up a little bit. You know, for Jacobian is partial omega, partial y, right? This is pretty much the definition. But you know the reaction rate omega is the summation for all the contribution from different reactions together, right? So if you can do this partial omega, you can do sigma I omega I. So omega I is a contribution for the reaction rate for each different reaction. So when you put all of them together, to give you the overall reaction rate, right? Partial y. Just keep in mind this omega I includes the effect of stoichiometric coefficient vectors, okay? And then this one, you can decompose this one to this. You can call this guy to be GI, which is the Jacobian matrix of the ith reaction. And if you think of this GI, how many non-zero patterns it can have? So for elementary reactions, each reaction only, let's say A plus B go to C plus D. That's the majority of the reaction type, right? So each reaction on average, it couples about 6 pairs of species. All right, so that's, if each reaction can only give you 6 non-zero entries, how many non-zero entries can you get for I reactions? It's 6I, right? So it's a linear function of number of reactions. That's why for analytic Jacobian, you clearly know the Jacobian has to be sparse, and also because number for reaction is proportional to the number of species. So this number of zero entry is also a linear function of number of species. If you get a large matrix, you know, number of entries is n squared. How many zero entries you have? It's order n. You know, the larger the n is, the sparser the matrix is. So therefore, if you get a larger mechanism, you get a much sparser matrix to deal with. So if you take advantage of the sparse pattern, you can always make the factorization for Jacobian a linear function. So that's critical. If you put all together, then this tells you for Jacobian evaluation, Jacobian factorization can all be done within linear time, which is comparable to a single rate evaluation. All right. So that makes the implicit solver actually not that much different from explicit solvers. Although to evaluate the Jacobian matrix, you still need to spend some time to evaluate Jacobian. Okay. So let's put this picture together. So basically, this is a scenario. What we can do for different solvers. If you want to develop different solvers, first of all, if you want to do explicit solver, you need to deal with reaction rate evaluation. You need to deal with diffusion. But if you take care of diffusion, we can show you later that this time can be gone, order 1. So there's no time for diffusion at all. So the only time it takes is order k, so linear function of k for implicit solver. It cannot be more efficient than that if you can do a long time step. So explicit solver, if you can get rid of stiffness, that's the most efficient solver you can have. Okay. If you have to use the implicit solver, you have to evaluate the Jacobian, but use analytic Jacobian and go linear. Okay. LU factorization, if you take advantage of a sparse pattern, it also go linear. So everything put together linear also. But this is maybe 3-4 times more consuming than the explicit solver per step. All right. So therefore, if you can somehow make explicit solver work for you, try at best to use the explicit solver. If you cannot do it, the best we can do is to use the implicit solver with 3-4 times the cost for explicit solver. That's the state of art for chemistry solvers. All right. And then among all of this, obviously you can see what else can we do to make simulation faster. Of course, to reduce n, to reduce k, right? Number of species. If you get a smaller model, it will be a lot of faster. So therefore, model reduction is to give you smaller k, smaller number of species to solve. And chemistry solver is, if you have to solve this number of species, 30, 40 species, how to make it most efficient. So the two things together, that's the best I can do right now. Okay. So the first part of this lecture, we're a little bit slow in the progress, is to reduce the model. Let's see, to reduce the size of the mechanism. Rather than 3,000 species, can we make it 300 or even 30? 30 is difficult. Okay, we will need you guys to work on it. But with large engine fields, large hydrocarbons, the best we can do right now is from a few thousand species, we can do about 100 species. So with NTC, low temperature chemistry. If we only deal with the high temperature flames, like flame holding, fast burning, relevant to the upper branch, so we need less than, let's say, about 40 species. That will be good enough to deal with high temperature problems. Okay. That's quite small already. Yeah, for model reduction, we get several major categories. The first one, we call it skeletal reduction. Well, when you see skeletal, basically you see a skeleton there, right? We only keep the most important one. Actually, in model reduction, you probably, the bones you think is the most important, but for the detailed chemistry guy, you think that probably is the most boring stuff. Actually, the state of art you work on in detailed chemistry, a lot of the reactions are gone through the reduction. So that's probably the best part. The meat is gone through the reduction. Okay, so the reduced model is quite boring. If you work on detailed chemistry, you probably don't like it. It's H plus O2 go to OH plus O. This kind of reaction. I don't know what we can do with it further. Okay, and then for skeletal reduction, we get a whole bunch of different methods. So one is called a sensitivity analysis. So sensitivity analysis is something very interesting. It's a scary word, right? If you have never used this, it sounds to be some big deal to use. But sensitivity analysis is simplest possible way anybody can do with almost anything. So a global sensitivity, let's say global sensitivity analysis. What you do is you want to get something, let's say reduced model or a new model, whatever, to work. You want to know how good the performance is, right? So if you throw away one guy, you want to see whether you mess up something. If you mess up something, you have to get the guy back. Okay, otherwise you just throw it away. So this is trial and error approach. So whatever turned out to be important, you have to keep it. Whatever turned out to be not important, you just throw it away. It's straightforward, right? So this is simply the way people can do for sensitivity analysis. It sounds to be so simple, but what's the problem for sensitivity analysis? Why not everybody just use sensitivity analysis for model reduction and that's it. As I said, anybody can do model reduction. Seriously. There's no energy barrier. You do model reduction. And the good news is whether you're good at math or bad at math, whether you can develop a good methodology or bad methodology, it doesn't matter for model reduction. As long as you use sensitivity analysis, or you always test the reduced model. Eventually, if the model is tested to be working, you get a working model. That's all. Sounds good? So if you want to work on reduced model, try it. And then just make sure you test it. Okay? Make sure it works for the targets you selected. And if it works, you can write a paper. You can just give it to people to use it. You can use it by yourself. It's all valid. It sounds like a good deal, right? But it sounds to be too good to be true. So what's the catch here? So why can't we just only use sensitivity analysis to deal with anything? Yeah.
So could it be that if you end up getting rid of a reaction, then you can totally destroy your model, even though let's say the amount of production was like small amount. So it found it to be insensitive because you moved it up and down, but still that small amount. Like let's say in the case of CO oxidation, a little bit of H will really change things.
I guess you are saying if you throw away something important, it will mess up something badly, right? Eventually you can't get a solution even. But in that case, if it's mess up things badly, you know you cannot throw it away. Just keep it. Yeah. So that's not a really issue. Actually, sensitivity analysis is, if something tested to be working, it's working. Simple like this. The key is how to get something working. You keep on trying, you will get something working. Okay, start from the detailed one. As long as you stay on the safe side, you always get a working model. But the key issue here is it will take a lot of time for sensitivity because you need to try a lot of different cases. You throw away one species or one reaction, you need to try all the different cases. How many different cases you need to try? You probably need to try 200 autoignition delay, 300 PSR, or 500 1D flame speed. So you put it all together, you delete one species, you need to run for 3 months to know whether this is a good move or not in the bad scenario. So, and the thing is, if it doesn't work, you need to get it back and try again over. How many possibilities you have, if you think how many possible tries you need to do to eventually get a reduced model, it's a combination of all different sequences. So the number of possible tries, it's more than the exponential function you can handle. So basically, there are a huge number of possible sequences you can do the elimination. You try ABC or ACB, CBA, whatever. Different sequences will give you different result. Okay, so even though you have some kind of ranking approach to rank this sequence, along the sequence is still not very efficient. It's still time consuming due to the large number of so-called validation you have to perform for sensitivity. So therefore, sensitivity is the easiest way anybody can use, but is probably the most time-consuming approach. So the simple way comes with a price. It takes a lot of time. Typically, you cannot afford it for large models. If you get a 3,000 species, just forget about this in the beginning. You need to throw in something more efficient. Okay, so yeah.
I think another limitation of sensitivity analysis is if you perform sensitivity analysis, you will compare the ignition delay with the case A and the case 2, case 1 and case 2, right? But the ignition delay definition of ignition delay is based on the, for example, 400 kelvins above the initial temperature. But if it's a low temperature condition or high temperature condition, we only compare the temperature, but what's the detailed kinetics process during that process is not captured. We just compare the temperature. I don't think for some detailed mechanism it cannot.
Understood. Basically, you meant if you do sensitivity analysis, you have a limited set of targets to compare. What if you have something else not included in this? But what we can argue is for sensitivity, suppose if we can get a large set of parameters, including all the possible cases that is relevant to our target. If you can include all the ignition delay time, the extension turning, flame speed, strain rate, whatever response, anything interesting to you, put this to target. Just suppose if your model works for everything, it works for everything. But this is ideal scenario. But in practical situations, you cannot possibly try all different scenarios. The best you can probably do, you can include 10, 20 ignition delay time, or some cases with 1 or 2 or 3 flame speed. That's the best people can do with limited computing power. With this limited target set, there's another issue coming out. It's called overfitting. If you do over reduction, although you can fit these several target parameters well, but if you change the condition a little bit, you will see it's totally messed up in somewhere else. So that is something related with over reduction. We have a little section to talk about this later. It's very difficult to avoid over reduction. Once you have over reduction, that's a big headache. I would suggest not to trust any models over reduced. Okay, because whatever fitting parameter tuning you do with it, it's very difficult to repair the model. All right, so if sensitivity doesn't work well, then we have to think of all different other ways for skeletal reduction. So I will spend some time to talk about a graph theory-based method called the DRG method, the direct relation graph. But the key is not to introduce you to this method. The key message I want to tell you for this skeletal reduction is, if you look at the reduction literature, there are tens or even hundreds of different methodologies. In term of a particular reduction method, we cannot see this method is correct or incorrect. Okay, there's never a concept of a wrong method or a correct method in model reduction, as long as you can do model validation. So you can use any method, valid or invalid, to get reduced model. As long as the validation result show is correct everywhere, the model is valid. Okay, the key difference it makes by using different methods. Some methods you see probably is better, some are not that good. Is if you can possibly make a method that get rid of the need for validation. That will help you a lot, because you will know you can control the error during the reduction, but you don't have to spend a lot of time to check everything. So in that case, you don't need to do the iteration. If it doesn't work, you need to change something iteratively, right? So therefore, if you have a good method, the good method means you can have the so-called a priori error control. So you can specify an error you need, and the error indeed can be bounded. That is a very good method because it can eliminate the need for sensitivity analysis. But if you have a method that cannot guarantee the error is bounded or limited, but you have to do the validation. Otherwise, there's a possibility the model doesn't work, right? So that makes a huge difference in different types of method. So the DRG method is one of the methods we designed to try to get rid of the sensitivity analysis. So if you have a 3,000 model, how could you design an efficient and also a trustable method you can use to quickly do some reduction, give you a smaller model, then you can run sensitivity analysis on it to further reduce it. So and this first step, the error control is absolutely the key. Okay, and the error control, it turned out to be some kind of a tricky issue. So it's probably the most important thing I want to discuss in the following: how to make sure the error falls below your threshold. Okay, you specify I can accept a 30% error, 20% error. How to guarantee it's below this line, or at least around this line. Okay, if you cannot control the error, game is over. You boil down to the sensitivity analysis. Okay, that's bad news. Another type of reduction method is called time scale based reduction. This time scale, of course, we know we have fast species, fast reaction, slow species, slow reactions. We know the fast guys in chemistry cannot always be fast. It's fast doing what? It cannot be something keep on going fast forever, right, by itself. So typically in chemistry, if something goes fast, it will get choked by something else. It quickly depletes itself like a radical, go to low concentration and follow somebody else. So this kind of exhausted fast process, typically it will give you some kind of algebraic equation, like a steady state approximation or partial equilibrium approximation. It will give you an algebraic equation to use to somehow evaluate some radicals concentration based on the major species concentration. So that can that one can be used for two purposes. First of all, for quasi-steady state approximation, you can use this approximation to get rid of number of transported variables. Number of species to be solved can be smaller. Okay. Secondly, the short time scale associated with the fast radical is gone. If every time step you solve the ODE together with the algebraic equation, then you don't have the short time scale associated with the radical. The stiffness is gone in this case. But then you have to solve the so-called the DAE problem. So DAE, literally, if you solve fully coupled DAE, that means differential algebraic equation systems. So in general, if you solve a general problem, you still need to use the implicit solver. But for chemistry problem, fortunately, for many models, many flames, we can possibly use very simple algebraic equation, which can be solved easily locally. So you don't need to solve the whole thing with the implicit scheme. It can still, like an embedded sub-procedure to deal with stiffness. So you do a little bit of operation locally to handle the short time scale. And it can get rid of the stiffness, but not giving you a lot of overhead. Okay, so time scale based is another one. So the third one is so-called high chem. I guess how many of you guys heard about this term? It's something new. Yeah, it's a new term which this name just came out this couple of years. It's by Professor Hai Wang at Stanford. He formalized this whole procedure. Basically, it's targeted for high temperature combustion problems, particularly for this high temperature condition when you get a large engine fuel. And this large molecules, first of all, before it's being oxidized, it has to crack into some intermediate species. And high temperature conditions, the fuel cracking will give you a lot of small molecules, right? Beta station will give you ethylene, propene, isobutene, etc. Sometimes some methane and some radicals also, hydrogen. So those small molecules, it form a soup. This soup can be oxidized next. The idea here is that this fuel cracking process at high temperature is very fast, and it doesn't matter much how many intermediate species you resolve for flames, because it typically doesn't matter too much. The fuel cracking layer is very thin in engine combustion. It doesn't cause much if you don't fully resolve this layer. Okay, but in addition, the oxidation of the subsequent small molecules, that is rate limiting. In that case, he lumped those fuel cracking reactions from large molecule and all the small ones gone to a small set of small molecules: ethylene, propene, isobutene, methane. Let's see, hydrogen, some radicals, H radical, H methyl radical, for example. Together with, if you have aromatics in it, you can probably get some toluene in it as a cracking product. Okay, so this way, the beauty of this is you can get rid of the whole big mess of the so-called the intermediate species, C5, C6, C10, C7, all those intermediate fragments, and then your small model will be pretty much an ethylene-based core together with a fuel cracking reaction. So that one, after reduction, it will give you about 30 to 40 species. It's quite compact, very small compared with the traditional reduction method. And the accuracy is remarkable. So I will show you some of the reduced model we just did for based on high chem. All right. There are also other methodologies I won't cover much. Tabulation is a very effective way to avoid repeated calculation. If you want to compute some similar flame conditions, you don't want to compute it every time, do the full evaluation, right? So if you compute this scenario, next time you redo it, you store it and then retrieve it if you use this condition. So for example, in ISAT, in situ adaptive tabulation, this is developed by Professor Pope. You can store this kind of ODE solution after one step in a table. So as long as the solution falls within the neighborhood of this stored solution, you can always use linear approximation to predict what happens at next time step. Okay, so this can avoid a lot of repeated ODE integration. So tabulation. Optimization, I don't quite like this word. Optimization, typically people refer this to over-reduced model. So if you are very aggressive, you see, I have to get a 15 species or 10 species reduced model. I can only have 20 reactions, 30 reactions. That's the best you can do. You can't possibly add any, or you are not allowed to add any more species. You surely end up with an over-reduced model, right? Over-reduced model, then people think, why don't we just tune the parameters to pull the model back so it can still predict the right ignition delay, the right flame speed, or probably the right everything. So why don't we use a 15 species model after tuning to fit everything? So is it possible at all? That's a question. Okay, so we will show some issue there later about this over-reduced model together with optimization. You need to be very, very careful about this. Otherwise, you can get this so-called a very bad overfitting issue. It can mess up something. So if you put this in a different flame condition, or if you optimize model in laminar or zero decays, if you put it in turbulent, you might find your model give very weird behavior in some other conditions. That's due to the so-called overfitting issue. Okay. And solver techniques is the key. We'll talk about this in the second part, but we won't talk too much. All right. We have a few more minutes. Let's talk about the next section for model reduction. So we spent quite a few minutes in the morning session to talk about the reaction state sampling, right? Because reduction, if you want to do reduction, you put together a set of this elementary reaction. This is not look like an elementary reaction, but you put all of them together to an ODE system. The reaction system, if you want to find who is important, who is not important, you always need to know the concentration information. We cannot just see this reaction is important solely based on the potential surface. If you work on quantum chemistry, let's see, you probably think by looking at the potential surface, in many cases we can determine this reaction is important or not important. In some extent it's possible, but in general cases, you do need to know the concentrations. As I said, I made an analogy in the morning. The potential surfaces acts like the roads, highways, connecting different places. But you do need to have the population information in the area to know which road will give you the largest traffic, the flux, right? Which road is important or not. Not necessarily you get a wide road, you get more flux or more traffic. That's not necessary. It depends on the concentration, right? So therefore, it's critical to find the right composition. You have to sample the relevant reaction states from some combustors. If you cannot possibly deal with sampling from 3D turbulent flame, because if you can simulate a 3D flame with 3,000 species, then you probably don't bother to do the model reduction anymore. If you cannot do detailed simulation, that means you have to use 0D reactors. For example, auto-ignition or stir reactor, maybe together with some 1D flames, let's say 1D premix flame or 1D non-premix flame, to get reaction states from those conditions. But you need to make sure the simple reactors you include in the sampling process. It pretty much covers the ballpark of the parameter space you will encounter in the turbulent flame you want to simulate. Okay, if you have a turbulent flame involving a lot of this flame extinction behavior, and if your model, again, it only is good for ignition delay time, then the reduced model may not work there at all. The burning rate may be totally wrong. So the sampling therefore is key. It's very important. So we look at this in the morning. Auto ignition, and we said, auto ignition is definitely important for IC engines. For IC engine, you compress something, you wait it to ignite, to auto ignite, right? The majority of the ignition delay time, this part is dominated by radical explosion. If you look at this, it's increasing exponentially because this is in log scale. So although temperature stays flat, it does something on the background. Okay, so how much time it takes for radical explosion, it determines the ignition delay. If you run shock tube, flow reactor, RCM, pretty much it matters how much time it takes to build up the radical pool. But for a lot of fast engine combustions, a lot of interesting things are squeezed in this very thin layer. It's like a step function. You do need to pull it up and look into the details of what happened in this very thin layer. So if you get a reduced model which is not valid for this part, you know you will have a risk when you use it to predict jet engine combustion. Okay. So to deal with that part, we added stirred reactor. So PSR problem. So PSR problem, as we said, I get an interesting question about this S-curve. So you guys are all familiar with S-curve, right? S-curve has 3 branches. So I guess I forgot to give a review for this in the morning. The upper branch, so this is called upper branch. This part is called upper branch. Upper branch basically is corresponding to a normal running condition for a combustor. If you get a flame going on, temperature is quite high. You have fast heat release there. The flow rate is high. So that's the condition for strongly burning case. If the jet engine is running, it's running on the upper branch. Okay, but if you keep on increasing the flow rate, say in jet fighter, somehow if you when you're let's say not the jet fighter, whatever airplane, if it's descending, okay, if it's descending, that means you don't need that much fuel. So you just add a little bit of fuel, reduce the fuel input, and then the gravity will just pull the aircraft very quickly go downward. So the flow rate is still high. You get a fast flow rate, so therefore the flow stays. The residence time of the flow in the combustor is reduced. It's very short, right? You don't have much fuel, and then with reduced residence time, it's easily you can lose the fire. The fire can go. So that is typically the lean blowout condition we talk about in engines. So that is corresponding to the extinction turning point. So that means you keep on reducing residence time. Reducing residence time means you are increasing the flow rate, right? Because residence time tau is proportional to volume over flow rate, right? If you have a higher flow rate, you get a shorter time to stay in the combustor. And then if time is too short, then combustion says, okay, that's the best I can do. I can't do faster. If you keep on increasing reducing the residence time, then the dilution process will take over and dominate chemical heat release, and then the combustor will quickly be diluted to the cold level, go down to the inlet. So it will jump down to the inlet. In that case, so once extinction happens, it looks like abrupt stuff. So the flame is suddenly gone, but it's not suddenly. It's still a very fast dilution process. If you stretch it up, you can see it's being diluted, but very quickly, because the mixing time here, residence time is let's see, in 10 microsecond, 100 microsecond, very short time. That short time is a blink of eye. The whole thing was just flashed out of the combustor. Okay, that's why it looks like a step function. But somehow, if you get a fluctuation, if you somewhere before you reach the end, and the flow is slowed down a little bit, then the combustor can possibly reignite. So it can possibly go down and then go up, jump back and forth near this condition. So therefore, in real combustor, near blowout condition, you see a lot of up and down, up and down. So extinction, local extinction, and it didn't fully extinguish, it can reignite. How much time it takes for reignition is typically also similar with this time scale here. It's 10 microsecond, 100 microsecond, that's the time. Because this reignition, it doesn't need to rebuild the radical pool. The radical pool is still there, okay? So that's what happens, as we said, all the jump up and down happens within these thin layers, okay? You don't go through this flat stage again, through reignition of the combustor. If it's gone, then it's gone. So, but what if the flame is gone in the combustor? Somehow you have to slow down dramatically to reignite it. The reignition, if you want to compress ignite it, it's almost not possible when the airplane is running. Typically, you need to put a spark there. You need to put a big spark, keep on sparking it. It will be very difficult, typically. So put a lot of energy there to push the system back to the upper branch, and then it can reignite. So once the flame is gone, it's a whole big issue how to bring it back, particularly if you get a high flow rate. If you get an enemy behind you, then you are in big trouble. Okay. This figure I showed before for one of the recent DNS, Alexei Palagonenko, he was in Naval Research Lab when he ran this DNS. So this is one of the extreme scale DNS run with real fuel. So we figured out this scanner, the heat release scanner. So if you look at this kind of scattering, this case is a very, very turbulent case. Carl-Lewis number is 1,000. So by the way, you all know what Carl-Lewis number is, right, in turbulent combustion. Carl-Lewis number is basically the ratio between the size of a small eddy in turbulence versus the size of the so-called flame thickness or reaction thickness squared. So that'll give you the Carl-Lewis number. All right. So if you have a high Carl-Lewis number, let me see, it's inverse. If you get a high Carl-Lewis number, that means the turbulence is very strong. You get a very small eddies, which can disturb the reaction structure. You don't get a laminar flame-like structure. You get a so-called broken reaction zone regime. So in this flame, we get a truly broken reaction zone flame. So reactions is everywhere. Okay, this one is pretty much is on the border in the turbulent combustion diagram, on the border of the flame regime and the broken reaction zone regime. So Carl-Lewis number 100 is somewhere borderline. But you look at the scatter plot. For this turbulent flame with fast mixing, the scanner actually agree quite well with stirred reactor type. And auto ignition, just keep in mind, this type of auto ignition is skewed compared with the scanner. And more importantly, for auto ignition, it takes a very long time to go through this stage, to traverse from low temperature to high temperature. This one is a barrier for auto ignition. But for high temperature conditions, this is skipped, and everything jump and run happens here. So therefore, for a strongly turbulent flame, it's more relevant to stirred reactor type of applications. If you do the model reduction based on sample reaction states from stirred reactor, the chances it works quite well for highly turbulent flames. So this is, in this sense, in many cases, you don't actually have to do real 3D flame simulations to do the sampling. You can use some of the representative 0D reactors as long as you cover the major reactor types. Okay. What we found is if we include auto ignition together with PSR, covering a wide enough equivalence ratio range, pressure range, and temperature range, the chances, most of the reactions important for a lot of turbulent flames are retained in the case. Okay. Furthermore, the reduced model for high temperature or turbulent flame cases frequently is much simpler compared with those needed for auto ignition. So for autoignition, you do need to include a lot of slow reactions, which is important for radical pool build-up. But for high-temperature applications, those guys are gone. You get a very small neat kernel involving only small molecules. So the model can be very, very small in that case. That's why a lot of people can use 15 species seriously for flame speed. If you're only interested in flame speed, you can use 15 species, get quite a good result. Okay, that's something about the sampling. Because we talked about it, let me see. So when do we? 4:15 is the next break, right? Yeah, that's about 10 more minutes. Let's quickly go through this stage. This section I didn't include it in the slides, but we'll just quickly go through it because it's something very important and also relevant to the S-curve we talk about. Okay, if you look at the S-curve behavior, S-curve here, I got a question earlier today during the break. There's a 3-branch, upper branch, lower branch, middle branch. Okay, we use solid line here to denote upper and lower branch because these are real conditions. You can run your engine or combustor here continuously. It's burning or it's no burning. So this is no flame case. If the flame is gone, you are running here. Okay, somewhere in the middle, it's called middle branch. Middle branch is not stable, and you said you can probably never put your flame running long time around this location. Either it jump upward or jump downward. Okay, now, so here comes two important points. This is the upper turning point for extinction, as we said. Lower turning point for ignition. Both turning points are key for model reduction. If you want to get a reduced model, which can work both for IC engines and for jet engines, you do need it to be valid to predict this turning and this turning. Both turning are important. And also for middle branch is seemingly, we don't have a 0D or laminar flame. It covers this part. So a lot of people think we don't need to sample anything from this regime, but that's not the case. In turbulent flame, you can frequently get transient behaviors, which is around this area. As we see in this plot. So this is the transposed upper turning point. So basically, this is the extinction point in PSR. In PSR, the extinction point. Upper branch is here, middle branch is here. Okay, you see, in the real flame, because it's a transient process, the sampled reaction state, indeed, it can cover both upper branch and the middle branch. So therefore, it's absolutely critical to sample some reaction states from the middle branch of a stir reactor. If you only make sure this part is correct, it's only halfly correct. So this part also needs to be correct to make the overall heat release right. All right. So that's some key thing to keep in mind. But physically, if we look at this one, I spent a few minutes to talk about what physically extinction and ignition is. As I said, ignition and extinction, they are both ignition process. It matters is how ignition occurs. For this one, lower ignition turning point, we can call it autoignition. You have to build up radical pool first and then run through thermal ignition. Okay, and for upper turning point, the first part is bypassed. You only need to worry about this thermal runaway stage, the fast burning stage. So therefore, this part is the scenario where radical pool is already there. You get a lot of H, OH, and O radicals. You put a fresh mixture in it, it will quickly be oxidized. So the reaction is a lot faster compared with this location. It differs by 2-3 order of magnitude in terms of time scale. Okay, so this pretty much the extinction limit. It tells you what the best chemistry can do. If you want chemistry to burn fast, you kind of push it around this limit, basically. This is the fastest you can burn in chemistry. You go along this curve, this pretty much gives you the fastest reaction. If you look at the S curves here, this is for hydrogen, and 3 different atmospheres. Okay, for this curve is corresponding to this curve. Middle curve is the middle curve. The 1 ATM is this curve. So what we did is we shifted all the S curves to be T minus T turning point. So basically 0 on this point indicated turning point for these three S curves, you can see the maximum heat release or maximum reaction rate occurs all close to the turning point. So therefore, the turning point, in a lot of cases, people think a flame extinguishes at the turning point. So therefore, reaction must be the slowest there, right? It's not the case. Extinction case is where reaction is the fastest. That's the fast limit for chemical reaction. So if you want to design your burner to burn fast, you want to push your burner to the extinction limit. And then at the same time, you will risk the flame extinction or blowout issue. Make sense? So for turbulent flame, how can you make it faster? You imagine there are two scenarios for flame to achieve ignition. One scenario is you can do auto-ignition to ignite the mixture. Suppose you preheat the mixture at inlet to 1000 Kelvin. Then when the mixture travels downstream, it will auto-ignite by itself, right? In this case, you do need to wait long enough. Somewhere further downstream, the mixture will ignite. That's so-called auto-igniting wave. We do have auto-igniting wave in IC engines to worry about. The second time is for laminar flame. If your temperature is low at the inlet, 300 Kelvin, it's not possible to ignite in 1,000 years, right? So what you can do is, in the flame zone, if you already have a flame, so the reaction zone has temperature, which is high, a lot of radical also. The radical will throw H and heat forward, upstream to the fresh mixture. And H is used to attack the fuel and to then preheat or force ignite the fresh mixture. In this case, this laminar flame propagation actually is a forced ignition process. It's not an auto-ignition process. Therefore, flame chemistry is only sensitive to the upper branch or middle branch of the S turning point. You will find you get a reduced model. If you get your reduced model based on upper and middle branch of the S curve, the chance is it also works for flame speed. You don't need to include NTC scheme or low temperature ignition delay time to make flame speed correct. Okay, and also for flame speed, that's why you can use smaller model to predict it. So if you're only interested in flame speed, the model can be smaller than otherwise. Okay. So this is the interesting thing about extinction, and also for extinction. So we talked about how the thing is jumped from the upper branch to lower branch, right? At this point, typically, if you look at this point it tells you something is balanced. So if you look at the combustion textbooks, people said something is balanced at the turning point. This turning point, and also if we go back, this turning point and this turning point, this something is competing with each other, and they get balanced. What get balanced? Chemistry versus loss get balanced. Okay, in both turning point, chemistry get balanced with loss, but then what actually exactly happens here? Because if you want to do model reduction, you do need to know what kind of equation I can write down for this turning point, right? If I only can verbally describe it, I want to get a reduced model for this turning point. How would you derive any model? So you do need some mathematical equation to use, right? It turned out if you dig into math, this point, people call this point to be so-called bifurcation points. Some of you may have heard about this terminology, bifurcation point. So what does that exactly mean? It means something goes cross zero at this point. Okay, what goes cross zero? It's an eigenvalue of the Jacobian. This sounds already a little bit more complicated. Let me see. So we talk about Jacobian here, right? So suppose this is steady state combustor. If you look at the equation, dy dt is source term. This source term include chemical reaction term and also mixing term. So steady state combustion means the right hand side reaches the equilibrium, goes zero, right? So you solve this algebraic equation, you can get this S curve response. Make sense? if this is equation governing this guy, so mathematically what happens to this point, we can figure this out by doing linear expansion or Taylor expansion at this point. What we do is we take this point, call it y0, tau 0. So by the way, y0 is the concentration temperature, tau 0 is the residence time. Okay. So by the way, this source term depends on the dependent variable and also parameter. Tau is a parameter. Tau typically you specify. Okay, you specify residence time and then you solve the set of variables. But if you do the linear expansion here, so I put a lot of equation. How about you spend a few seconds to look at the equation to see if it makes sense. So that means we expand this term, source term, around this turning point. What happens is this turning point is GYO tau O, its value here. And this is a Jacobian, or the first order derivative. So partial G, partial Y, times Y minus Y0. That means how much difference between Y and Y0 between these 2 points. And this is partial G, partial tau. So this is in multivariate calculus. So this is a linear or Taylor expansion, first order Taylor expansion, right? Make sense? I just want, if you get questions, make sure you ask, because this is something we need to know to understand this. So if we take this point and this point, both are on the S curve. So this is 0, this is 0, because along this curve, the short term are all 0, right? If they are both 0, that means this term together will be 0. So that means this term will be 0 together, right? What you can do is you can just put this together. This is delta tau. This is delta y. You can put delta y divided by delta tau to be approximately dy d tau. That's if you change tau, how much change of solution will give you. So what determines this change? Obviously, it's this term. So basically, it's Jacobian inverse. So this is the inverse of Jacobian. This is how sensitive is the source term to flow rate. Obviously, the sensitivity for the source term to flow rate is a finite number, because if you change residence time, your mixing term changes, right? But chemistry doesn't matter. So this is a finite number. This is a finite number. But at the turning point, this tells you this number has to be infinity, right? Partial dy d tau has to be infinity. How can you make it an infinity? The only possibility is the Jacobian must be singular. It cannot be inversed. So the inversion will give you an infinity. So therefore, mathematically, it tells you Jacobian becomes singular at the turning point, or extinction state, or ignition state. This is a very important message. Because what does it mean by Jacobian become singular? Jacobian becomes singular. Singular Jacobian, if you think of a set of linear equation, it only happens when some equation keep on changing until this equation becomes redundant to something else. Okay, so because this is a nonlinear problem, if you go along this S curve, so you get a one set of equation, but the equation keep on rotating because it's nonlinear. Across this point, one equation becomes redundant to others. So you lose one equation. So the system is not well defined at this point. So if you try to solve this turning point directly, you cannot possibly get an answer with this set of equations, because this set of equations, it doesn't give you enough number of equations to solve y. All right. So what you have to do is you have to add another set of equation to describe what happens at turning point. So therefore, if you want to solve extinction time or ignition time through PSR, it's not possible that you directly solve the original PSR equation. You use Chemical 2 or use Chemical Pro. There's no way you can do it. There are different ways you can do it. You can, for this one, you have to change the equations. One way you can rotate the system, so it's just a transpose curve. Rather than solving T concentration, temperature concentration, you can fix temperature. You can solve concentration and tau. Use tau as a variable. That one will make it like not a singular problem anymore. Okay, so it's a lot of trouble to get a turning point, but turning point is very important for this so-called limit phenomena, for ignition or for extinction problems. So mathematically, it gives you a whole lot of trouble. But it also gives you some interesting information because you see one of the eigenvalue goes 0. That is the definition for singular Jacobian, right? What does it mean that lambda goes 0? If you dig into the physical meaning for this, it gives you a lot of interesting information. So let's look at this. So Jacobian, keep in mind, you have contribution from chemical reaction, right? So dTg is source term including chemical source term and a mixing term. So G is equal to omega plus S. So therefore Jacobian you can decompose to the contribution from chemical source term and the contribution from mixing term. So we can call this chemical Jacobian to J omega and mixing Jacobian to JS. If you do the eigendecomposition, you know B is left eigenvector, A is the right eigenvector. By the way, B is a row vector and A is a column vector. So typically the eigenvector we talk about is A vector. They appear by pairs. You have a pair of eigenvector. You get a right one, you have a left one. They can have different units or dimension, but when you use them in pairs, this guy take care of the normalization. Okay, so therefore always try to use A and B in pair. If somebody only give you one eigenvector, you will see a lot of trouble using it. So, but when you do the projection, so B dot G dot A, you give you the eigenvalue, right? You can decompose the eigenvalue to two terms. One from B dot G omega dot A. The other is B dot G mixing dot A. So that one will give you one scalar. That means the part of eigenvalue from chemical source term and the part of eigenvalue from mixing term. You get two contributions. These two must be equal to each other. That means lambda omega must be equal to lambda omega s at the turning point. So that is actually what we always talk about, chemistry balance loss at a turning point. But what chemistry of this guy, chemistry loss of this guy. If you look at the dimension for lambda, so what is the dimension for eigenvalue in the Jacobian? It's 1 over time, right? So the eigenvalue has a unit of 1 over time. That's very important. So the eigenvalue tells you a time scale. So therefore, this lambda omega tells you a critical chemical time scale. We always keep on talking about the time scale, chemical time scale. But if you think chemistry has a lot of time scales involved, if you get 10 species, you get 10 time scales. If you get 1,000 species, you get 1,000 times scales. Okay, and then we always talk about we define Dunkel number or whatever number, dimensionless number based on chemical time scale and mixing time scale. But which time scale do we talk about in terms of ignition, in terms of extinction? And this one tells you the time scale we talk about for ignition extinction is this guy. All right. So let's look further to see what happened to this. This is a very important guy, because if you look at lambda s is a time scale for mixing or for loss. In nature, if you look at the formulation, sometimes it's from diffusion, sometimes it's from the homogeneous mixing in PSR. If you look at the format of the mixing Jacobian, it always gives you a negative eigenvalue. So lambda s is always negative by nature. Okay, so in diffusion, because it's dissipative in nature, you get a negative time scale. In PSR, it's 1 over tau. Okay, but it's negative. So that means the loss is always give you some kind of negative eigenvalue. Or another word, if you don't have chemical reaction, the system will not be unstable. So stir reactor will not, because you get eigenvalue to be negative for all different cases. You get perturbation, the system will return to the stable solution on the upper branch or lower branch. But if lambda s is negative, that'll tell you lambda omega, this chemical eigenvalue, must be positive. Just think about this. If you get a positive eigenvalue, what does it mean? That means something try to go exponentially. Okay, so in linear algebra, if you get a negative eigenvalue, the thing try to decay, approach some constant. For equilibrium problem, we get a negative eigenvalues everywhere. It approaches the equilibrium, right? But if you get a positive eigenvalue, somebody was very energetic is try to explode. you get this kind of behavior or this kind of behavior, either go up or go down exponentially. This is a very important feature for combustible systems, because when we say combustion, we are talking about something can explode. If the combustion can only occur in this way, there's no fun. Linear combustion, there's no fun. We are dealing with combustion problem. It's so much fun just because it has this explosive behavior. Okay, it can explode, and once it's becoming explosive, it's difficult to handle it because it's so fast, right? So, and this one tells you across this turning point, the mixture become explosive because it shows positive eigenvalue. So therefore, the necessary condition for you to have an extinction problem is you have an explosive mixture. But physically, what you can imagine, when can you have, I spent too much time, I guess. Let me just take one more minute to finish this topic. So physically, how can mixture become explosive? If it's totally product, high temperature, but all water, CO2, it cannot explode anymore, right? It can only be explosive if there's enough fresh reactant. So you have to have unreacted fuels there for the mixture to be explosive. And for this case, it's becoming explosive because approaching the turning point, time is so short, the reaction cannot be complete. So you have a lot of left over for the reaction, the reactants. A lot of fuel is left behind. And the mixture becomes so explosive. You have the reactant and you have the temperature. That's why it can be fast exploding. And this kind of scenario will give you this turning point. So therefore, you can see the extinction point is where the mixture becomes most explosive chemically. Make sense? Using this scenario, we can actually, if we look at a lot of different terminal flames, we can find a lot of interesting findings. I will show you some of the explosive mode analysis later. So we have different modes. We have an explosive mode, we have a decay mode. They will give you different tools to use for analyzing flow and for model reduction. But let's take a break and then we come back in 15 minutes. Okay.